Good morning. Welcome. Thank you for joining me. We shift the time a little bit, but you watching all of the announcements and you found me, which is a really good sign of my students. Okay, that's me. Again, thank you for joining me, and let's cover section 10.7. I hope everything is going well and everybody is still working. You may use the chat box do you remember? You may use the chat box to tell me something. Hello, yes, thank you, Deepan. Thank you. Okay, that's me. We do have, I'm assuming that everybody can hear me. Yes, and everybody is saying hello. We have this week, we have next week for the new material, and then we will review everything, finalize by reviewing everything following week, which will be, yes, in 3 weeks. And the final test will be open. That's when please check everything what is available for you, maybe to submit, maybe to resubmit. About resubmitting, I'm only referring to the discussion. Because we still have a due dates, we still have to keep up with the calendar, but check the discussions, check the discussions. If you didn't, for instance, get the full credit, or you think you will not get a full credit, because if you read your post, your input, and you think it's not like worth it, the full credit, try to add something, anything, Try to add anything. You can go through all of the discussions. They are still open. Yes, they are still open. Okay, I'm always repeating this because I want you to, to earn this, like this assignment, at least this one for 100%. Okay, what we will do? We will talk about another part of the power series. We will talk about the Taylor series, which will be next section, but today we will limit to the Taylor's polynomial. And I hope you saw the session before this one. If not, you can look after this session, because the formula that we will be using today, I will just grab the formula, but I think I make like a 5 or maybe 10 minutes like video proving where the formula comes from. Okay, that's me. Please check. It's interesting. It's a nice pattern. Okay, that's what we will do. Let me actually really quickly come back. Okay, let's look at this. I don't know if I hope I didn't mess up my presentation. Okay, really quick question. Aravinda, yes? If it's quick, I can answer. If it's long, we don't have time. What are you asking? What is the final? Oh, we will have the review. That's mean final definitely covers everything. Final test is accumulative and covers everything. You may start reviewing exam 1 and exam 2. Yeah. And then we can just, in the last week, we can just review the new material after exam 2. Yeah, that's mean definitely material for exam 1 and exam 2. That's mean that's what you can start, because this will be like almost like half of the test of the final. Yes, everything from week 1. It has to be cumulative. Okay, let's see, because we have lots of work today. Yes, that was good, quick question. What you learned last week? Last week, you learned about the power series, and we talk about the interval of convergence, radius of convergence, but also important section of the power series was the power series representation. Yeah? And we learned that some function, we may get the power series representation. Basically, what is power series? Power series is like a polynomial with infinitely many terms and of infinite degree. Yeah, that's the power series. And polynomials are just the addition, subtraction of the power functions, the easiest functions. Yeah, the graph is nice and smooth, so easy. Just the multiplication is like involved, maybe division, just the elementary algebra. And now we know how helpful it is to rewrite different type of functions for different reason as a polynomial, as a power series. And we learned this one, yes, the geometric one. We remember that this rational function 1 over 1 minus x has the power series representation and is this one, x to the power of n. We remember the geometric, yes, the geometric one. When we will expand, it will be x to the power of 0, which is 1, plus x squared, plus x cubed, and so on. And these power series, we may approximate that function. The same, we learn more functions, but I just type this one as an example, arctangent of x. It's not extremely complicated function, but we don't know some of the values. Yeah, like the same actually like this one, sine of x, cosine of x, e to the x. For some values, we can evaluate a function, but for maybe some decimals, we will not know what is sine of, like, let's say pi over 13, for instance, yeah? Or what is arctangent of like pi over 13, yeah? The angle. We don't know. Actually, it's the arctangent. That's mean what is arctangent of like 7? Yeah, we don't know. That's mean we definitely need some numerical approximation. And then polynomial, the polynomial approximation is good. Yeah, that means that's the reason that we need, even if we think the power series like sigma is way complicated, it's not. It's actually giving us like more option to solve some problems. Okay. To the point, that we know these formulas, yeah, they are important. Now, but what we did, this was our tool, basically. Yes, everything what was related to that formula, 1 over 1 minus x. Like we may differentiate or integrate. Actually, by integrating, we got arctangent, yes, because we remember our integral of this is inverse tangent, arc, tan of x, plus the constant value. And then we made that integrand, we may rewrite as a sigma, we know how to integrate, and we actually, that's the result, integrating as a power series. But as I said, we have more functions, sine of x, cosine of x, for instance, e to the x, natural log of 1 minus x, and many others, that it will be also helpful to have a power series expansion. Yeah, for, as I said, just to evaluate some values, or maybe another like group of functions, for instance, e to the x squared, sine of x squared. It will be so difficult to integrate, for instance. But if we will get the sigma notation, the power series representation, we know how to integrate or differentiate power series. Yeah? We remember from last week, it's actually just the power function. How to integrate x to the power of n, or how to differentiate. That's what I'm saying. We know this, so easy. Yeah? Just the beginning of calculus, it's calc 1. Yeah? That means the point is we would like to get sigma notation, power series representation. And since all of my examples, like here, they're not really related to that formula, yes, we will be not able to use this like we did in the last week, even through differentiation or integration or any other like algebraic manipulation. Yeah, we will not get the form of sine of x, cosine of x, or the other. That's what we need. We need a formula. We need a general formula, yes, for the power series. And that's what I did in the video. That's me. I will quickly give you the formula. Yes, let's see. That means this is, yeah, this is the general, the most general form of the power series. Function can be represented as a power series. We still need more details to be like exact mathematically, but yeah, certain function can have power series expansion, they equal to, because they are convergent. But this is the general form, c sub n x minus a to the power of n. And what we need in order to be able to get the power series expansion almost for any function, we need a formula for that coefficient. We need a formula for c sub n. Okay, we need that formula. And I did the whole process, but please watch the video, okay? It's just 5 minutes or maybe, yeah? I did the process. I did a couple of derivatives, another derivative, some coefficients, okay? And the formula is like this one, okay? But please check the video. It's just 5 minutes, but because I would like to spend more on the questions. Nth derivative at a is the center over n factorial. And now we can see, we can take almost any function and try to find the nth derivative at the center, divide by n factorial. That means that's important formula. Yeah? Check where the formula come from. But couple of names. If we take again this general form, and if I replace C sub n with this formula, we will get this or this form. Okay, we can see nth derivative at a over n factorial and the power form x minus a to the power of n. And this series is called Taylor series, just because of that formula. Was developed by the English mathematician Brooke Taylor, and we calling Taylor series. Okay, centered at a, centered at a. Yeah, that's it. Now, if we have center 0, which we can call special case of a Taylor series, yeah, we can see center 0, it will look like this. We actually call Maclaurin series, yeah, just to know. Maclaurin is another British, or let's be more specific, Scottish mathematician, Colin Maclaurin, and they work, yes, they work independently. Maclaurin mainly focus on the centered 0, but it's the same thing. Even if we say Taylor series centered at 0, it's still fine. But when we say Maclaurin series, definitely must be centered 0. Which all of the power, like power series expansion from last week, even if we didn't use that formula directly, but all of them are related to this formula. And all of them that are centered at 0, we can also call Maclaurin series, okay? But that formula, okay, it's important. Now, so far, I'm just saying about Taylor series, Maclaurin series. We can see dots, 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 which you will have a session tomorrow and you will talk about the series. We will start with a little bit easier, yes? We will just take final number of terms, which instead of taking the entire series, we will take like partial sum, I can call, but the partial sum will be called Taylor's polynomial. Yeah, just finite number of terms. That means let's see this one. You will also discuss this later in section 10.8, but let's look at this. In general, function f of x is the sum of its Taylor series. That means this is the formula, t sub n plus r sub n. And t sub n, we will call like just partial sum, but we will call Taylor polynomial degree n, because we will start with 0 and stop at n, x minus a to the power of n. And then we still keep working if we talking about the series n plus 1 and then infinity. And then we have lots of important details like this. We call this as a remainder. Remainder must go to 0. We have to have some, yes, we have to have convergence, but even if there is no guarantee that the Taylor series converges, like equals exactly to f of x. We have a couple of things, but in general, when we have analytic function, what we basically need from the function, since we have the nth derivative, we can get Taylor series expansion for the function if function is infinitely many times differentiable. Yes, function supposed to have infinitely many derivatives. If function doesn't have, then we have a problem. Something can get wrong. But we will focus on the functions. Like, what about sine of x? What do you think? Can we differentiate forever? Please confirm. What about cosine of x? What about e to the x? Can we get first derivative, second derivative, and so on? Yeah, that's a good, nice examples. Yeah? Yes, we can. They are continuous. Yeah, they are differentiable. Like they have infinitely many derivatives. Yeah, at all of the points, because domain is all of the points. But points, we can always get some restriction, but yeah. Yes, but what we will do, we will just focus on Taylor's polynomial. Yeah, that means not everything, we will just say Taylor's polynomial. So we can take a function and find a Taylor polynomial. And of course, the application is we can approximate. Yes, we can approximate function by Taylor polynomials. Okay, some definition, theorems. Okay, Taylor's polynomial, that's what we're supposed to start. One more time. Okay, don't worry for other things, but this is, yes, we can see, this is the Taylor polynomial. You may notice we do not have 3 dots at the end, we just stop at n. If I want the 5th degree polynomial, for instance, we will keep working with this formula and stop at the term x minus a to the power of 5. If I want 10th degree, we will keep working and we will stop at x minus a to the power of 10. Okay? That's the Taylor polynomial, which in general we can say is a partial sum, just a finite number of terms. Okay. Again, this is more related because it's so strictly connected to the series, but don't worry, 10.8. Okay. Okay, now one more time, I copy, that means this is the sigma notation. You may notice it's not infinity, it's from 0 to n, and that's the expanded form, n, because it's t sub n. And for instance, let's see, t sub 0 will indicate just the function. Yeah, that means if n, if this is 0, it's just the function. T sub 1 will indicate the 1st degree Taylor polynomial. Then I have to copy that number of terms that I have to stop at x to the power of 1, x to the power of 1. Okay, and I copy the 1st term because it's constant, and the 2nd term is this one, but it's x to the power of 1. That means we may also notice 2 terms are giving us t sub 1, because this number 0, this index 0, 1, 2, 3 doesn't really indicate number of terms, it indicates the degree. Yes, sometimes we can have more terms, less terms, depends. But t sub 1, we definitely have 2 terms. Doesn't mean that we're taking just 1 term. Yeah? No, degree. And do you actually recognize the 2nd line? The 1st degree Taylor polynomial looks like a linearization from Calc 1. Who recognized this formula? Yeah, it's a linearization. Because it is line. But this came from the Taylor. We got a little bit different way, but this is a Taylor polynomial, degree 1. And now we can expand our approximation, linearization. We can approximate a function not only by the line, maybe by the 2nd degree, or maybe 3rd degree, maybe 4th, maybe 10th degree polynomial. But it will be still polynomial. And that's what we can see. This is the quadratic approximation, this is the 3rd degree, and so on. But they are Taylor's polynomial. Okay, cool. It's cool. Everything is connected. Okay. Let's start working. Find the following Taylor polynomials: t sub 0, t sub 1, t sub 2, t sub 3. That means 0 is just the function. 1st degree, 2nd degree, 3rd degree for the function e to the x centered at 0. Okay, that's what I will do. I will say e to the x, okay, can be approximated by Taylor's. Okay, let's do this one. Starting from 0, ending with n, nth derivative at 0 over n factorial x minus 0 to the power of n. Okay, and then let's get the expanded form. If n is 0, we will have just f of 0. Then if n is 1, I have to have I, the other I, and I, because I is changing from 0 to n. N is the last name, just the index, just the notation. Okay, 1st derivative at 0, 1 factorial x to the power of 1. second derivative at 0, 2 factorial, x to the power of 2, and so on. Third derivative at 0, 3 factorial, x cubed. Okay, and actually, I can keep working, but then I can say nth derivative at 0, n factorial, x to the power of n. But what we have to do, we have to find t sub 0 is just the first. Wait a minute. Yes, it's just the value of the function at 0. Value of the function at 0 is just 1. Okay, actually, let's, no. Let's find out all of these values. Let's find f of 0, and then we will list the polynomials respectively. We have to find the first derivative, second derivative, third derivative at 0. Okay, so what we can maybe build some, I would like to organize, I will leave one line, n, and then function, and then function at the center. Makes sense. This will be 0, just the function, first derivative, second derivative, third derivative. This is actually a nice function. Maybe nth derivative. Not always we can find this pattern. Okay, function is e to the x. Okay, first derivative. What's the first derivative of e to the x? Yeah, of course, e to the x, second derivative, third derivative, and even the nth derivative. Yeah, that's easy function. At 0, it will be 1, 1, 1, 1. That means actually we can say, yes, this is from 0 to n, I derivative at 0 is just 1. This will be I factorial x to the power of I. Or even shorter, and x to the power of I over I factorial. Yeah. But let's expand this. Let's expand. If, or maybe we can substitute f of 0. Yes, f of 0, it's e to the power of 0 is 1. Derivative at 0 is also 1. That means 1 over 1 factorial. Second derivative at 0 is also 1 over 2 factorial. And then third derivative at 0 is also 1. Actually, any derivative at 0 will be 1. 1 over n factorial x to the power of n. That's how. But now let's actually get, what is this? What's the first degree, second degree, and the third degree? How we can approximate? Okay, what is t sub 0? Now we have everything. Just the 0 degree, which is basically the value of the function. Yeah, it will be just 1. Just 1. What is the first degree polynomial? Oh yeah, depend is here. I didn't see the message. It will be 1 plus x. Because it's 1 plus 1 over 1 factorial is x. Okay. What about the second degree polynomial? 1 plus x plus 1/2 x squared. Correct? I just have to list all of the terms up to x squared. And x cubed, 1x, x squared. And what's the coefficient of x cubed? What's the coefficient of x cubed? Please simplify. Oh, yes, 1/6. Okay. And then we can keep working. 4th degree, if I ask you for the 10th degree, you can give me the values. Yes, 1/6, 1/6. Rachel is 3 factorial, but yes, yeah, it's, yeah. Okay, and that's we can see now instead of e to the x, we may approximate function e to the x, okay, by this polynomials. Let's see, I have the graphs. Oh, actually, oh, where are my graphs? Look at this. Yeah? The pink curve is e to the x. And now this is just the line, even the line, centered 0. That means everything is, yeah, with the good approximation is near 0. When we're going away, function goes a little bit different direction, is changing the slope. But we can see even the linearization, even the tangent line, the first degree Taylor polynomial looks so similar. The yellow is the quadratic, the second degree approximation, second degree Taylor polynomial. Blue is the third degree. Yeah? And if we increase the degree, the polynomials, they will behave almost like so closely to e to the x. The exponential, and then we can use it. Instead of evaluating e to the power of a certain number, we can take these polynomials. Okay, another question. Oh, okay, I have a table. Find the fifth degree Taylor polynomial for the function ln of x centered at 1. Oh, well, do you see we have to find fifth derivative? I mean 5, the fifth derivative, and then derivatives at the center. Okay, that's me what I will do. Natural ln of x, and I can say this. Let's keep, maybe not, the sigma notation. From 0 to n, okay. Actually, let me skip for you because I wanted to use, okay, that's mean the Taylor's formula, Taylor's coefficient formula. Value of the function at 1, value of the first derivative at 1, 1 factorial x minus 1 to the power of 1. Value of the second derivative at 1, 2 factorial x minus 1 to the power of 2. Value of the third derivative at 1, 3 factorial x minus 1 cube. Value of the fourth derivative at 1, 4 factorial x minus 1 to the power of 4, value of the fifth derivative at 1, 5 factorial x minus 1 to the power of 5, because I need the fifth. Do you like it? And I can tell you, I did this for a reason. I really would like you to do exactly the same. Yeah, it will take a minute, but say aloud. Yes, like value of the function at 1, value of the first derivative over 1 factorial x minus 1 to the power of 1, value of the second derivative at 1 over 2 factorial x minus 1 to the power of 2, and so on. Then you will remember. Then your final test will be like this. You will not miss the question with the Taylor and Maclaren, polynomials and series. Okay, it's a practice. It's a practice. It's an exercise. Okay, now we need the values. Let's use the table. Function is ln of x. Please help me. First derivative. I'm looking, yes, thank you for helping. 1 over x. Second derivative. You have to be careful. Is this correct? Yes, thank you, Deepan, thank you, Rachel. Another derivative. Yes, positive, okay. Another one. It will be like this. -6, okay. And one more. 24 to the power of 5. Please confirm, because it's negative positive, this will be positive. Okay, thank you. And now we have to substitute 1. Natural log of 1 is 0. 1 over 1 is 1, -1, +2, -6, 24. Nice. And now let's take these values and substitute. That means this will be, that's actually 0. We don't even have to write. First derivative is 1. I can maybe write this. Second derivative is -1. That means it will be -1 over 2 x minus, and then +2. I'm trying to simplify. -6 and +24. 5 factorial is 120. Okay, we can still simplify and see some pattern, but we don't have to look at the pattern. This will be x minus 1. this is simplify, this will be 1/3. You see this. This will be negative 1/4. It's definitely alternating. And this one will be 1/5. This means the denominators of the coefficient match to the power. 1/2, 2, 3, 3, 4, 4, 5, 5. But it's no, this is the 5th degree Taylor polynomial for the function natural log of n. Oh, natural log of x. Oh, I think I got used to, I'm preparing the final, the sequences. ln of x, of course, ln of x. Okay, but this is the polynomial. That means please make sure that you know how to find out the polynomial. Okay, and now we can take natural log of x and approximate by the 5th. I don't have the graph, but probably will be good approximation centered at 1. Yes, near 1. Function natural log of x and that 5th degree polynomial, they will look almost the same. Yeah. Okay. That means that's actually, yeah, that's the Taylor's polynomial. But let's do another thing. Do I have it? Okay. That's mean what we have. Since we know how to find the polynomial, important because it's helpful. Now we can use this polynomial to approximate a function. But if I will use the exact value, let's say exact value, always the exact value are a little bit different than the approximation. That's we do have hopefully a small error in this approximation. And another part of this section is asking us to estimate that size of the error. Okay, we know how to do it because it will be so similar to the alternating series estimation theorem. But we will call Taylor's inequality or the error bound, like theorem. Okay, that means let's see. We know the polynomials. Check. Okay. That means now what I have. Let's see. Okay, when we have, what this is the Taylor polynomial. But let's assume that we have a Taylor-like series. I mean, we have the entire function, everything. Yeah, that means let's maybe that line, this will represent like everything, the exact value. Yeah, or even I can even say the, I don't know, really high degree polynomial, but no, the exact value, f of x. I can call this f of x. But that line will represent the nth degree Taylor polynomial. And we're trying to approximate the red line with the green line. We can see they are not, yes, they are almost the same, but we do have a small difference. Let's call R of m. We have this error, this reminder, because if I take the entire function, f of x, minus the green one, the approximation, we have this error. And the point is we have to, without having the entire value, like the red one, we have to still estimate, because if we will have the red line, the red value, we can get the red value minus the green value, we will have the size of the error. Now, without having the exact value, because that's impossible, having only the approximation, we have to estimate the size of this error. And we have a theorem. Let's see. Yeah, we can even use, yes, we can even, it's similar to alternating series like estimation theorem, but we will use the method 3, which is the same. Taylor's inequality or the error bound, that's the same thing. Depends on the textbook, depends on the labels. Okay, and I will provide this. I will not really prove it. Okay, don't worry, don't worry. If you hopefully, actually, no, let me ask for the alternation. Like, do you remember the alternating series estimation theorem? Because then will be easier. We can make some connection. Like we remember we had the sum minus the partial sum. Yeah, that was the, let me remove this. That means this is our, this is the error. Yeah, because the sum is the entire sum minus the approximation by the partial sum is the error. And always, yeah, do you remember the error was less than the next term that we didn't use it, b sub n plus 1. Do you remember? Like, because s sub n means that we added up to like b sub 1, b sub 2, b sub 3, up to b sub n. That's the partial sum. And we were telling that the partial sum is almost the same like the entire sum. But that error was always less than the next term that we didn't use in the partial sum. Yeah, we remember that? B sub n plus 1. Now, the Taylor's inequality or the error bound, it's exactly the same. That difference, yes, this difference, f of x, the entire minus the approximation by Taylor's polynomial, we will call the error, the remainder, is less or equal to than the next term that we didn't use in the Taylor polynomial degree n. That means the term, the formula that we learned today is the nth derivative. That means we will have the next derivative, yeah, over not n factorial, over the next number, n plus 1 factorial, and x minus the center to the power of not n, n plus 1, the next one, because we use nth degree to approximate. Then the error is less than the next term, n plus 1, n plus 1, n plus 1, and this is just the formula. Okay. The only thing you will probably see, this is the next one. That means if we use the approximation by the 5th degree Taylor polynomial, this will be 6. This will be 6. Oh, I will put n plus 1 just as a general form. But, and this will be the next, yeah, this will be 6 to the power of 6 and the 6th derivative, the next derivative. But in the textbook, you will probably see like quantity k. K or m, I think we have k. But what k means? It means that we have to find the next derivative. The problem is we have to like maximize the value of this derivative to maximize this estimation. Right? We will do an example. Right? But this is the error bound theorem or the Taylor's inequality. Okay, so now nothing is, we're not scary. We understand everything. Okay, we can see it's written a little bit different, but it's the same thing. That difference, that error is less than the next term. N plus 1 factorial, n plus 1, and k, but k is the n plus 1 derivative, but it's the maximum value on the given interval. Okay, let's do the exercise. You may pause the video, maybe you can digest, okay? But let's do an example. That means I have, look at this nice settings, and we can also do on the test, maybe we will, I don't know, we can ask you for instance, the 3rd degree Taylor polynomial, and then next question, use Taylor's inequality to estimate the accuracy of approximating a function by the 3rd degree Taylor polynomial, and it's the same function that we just worked on. Okay, let's do it. Important set of the questions. That means this is the last 2 questions for today. Okay, this one easy, right? But let's do the work. Maybe I can do this. 3rd degree Taylor polynomial. You know what you have to do. A centered at 0, value of the function at 0, value of the 1st derivative at 0, 1 factorial x to the power of 1, value of the 2nd derivative at 0, oh, x to the power of 2, we're not subtracting 0, and 3rd derivative at 0, 3 factorial x cubed. We don't need that parenthesis, but okay, let's find it. N, oh, 0, 1, 2, 3, oh, okay. This is function, which is e to the power of, oh, I don't know if I can see 1 over x over 2. And this will be at 0, the same value. Okay, you have to help me with the derivatives. We need 1, 2, and 3. derivative of e to the power of any number is the same function, correct, times derivative of this inner function. What's the derivative of the exponent? 1 plus x over 2 times 1/2. Okay, and then I will repeat this. E to the power of this times 1/2 times 1/2, 1/4. E to the power of this times 1/2, 1/4, 1/8. Okay, and then when we substitute 0, it will be e to the power of 1, 1/2 e to the power of 1, 1/4 e to the power of 1, and 1/8 e to the power of 1. Okay, which answer is correct? This is a real test for my students. If you're watching this later, you can also answer the question now, and then be honest to yourself if you answer correctly or not. Which answer is correct? We have almost everything here. I know, and it's the most common mistake. Yes, the most common mistake. Why the option A is not a good answer? What we still missing? Let me finish the question. D is the correct answer? No. Let's finish. Do you remember? We have to say aloud to ourselves. B is the correct answer. Yes. F at 0 is E. And then this is 1/2. Okay, I can put x to the power of 1. E, the second is e to the, but we do have 2 factorials. And then we have 8 and we have 3 factorials. Okay, let me highlight this. This one is part of the formula. Yeah, 1 factorial is not affecting a number. Okay, that means I think this will be the correct answer. We still have to, I know that we have, these are just the derivatives. We're still dividing by respectively the factorials, 1, 2, 3, 4, and so on. Okay, please do not miss this one. You will not miss it. Okay, that's, we have this polynomial, perfect. We can approximate function e to the power of that by the 3rd degree Taylor polynomial. But we do have, yes, a little error. Now let's evaluate the error. The center is 0, and this question is letting us to go like 2 units away, from -2 to 2. That means how good is the approximation on that interval, yeah? Even if we're going away exactly 2 or exactly -2. I mean 2 either way. Okay, that's what we're doing. We're approximating a function by the 3rd degree Taylor polynomial. Okay, function is of course this one. We know that this error, this difference, is less than the next term, which this will be 4 factorial, x minus the center, but center is 0 to the power of 4, and quantity k. K is also the 4th derivative. I can maybe say this. It's the 4th derivative, but it's the maximum value. Value of this derivative on that interval. Okay, that's we need the 4th derivative. What's the 4th derivative? Let's come back. Do you see? I make the room. What will be the 4th derivative? E to the power of 1 plus x over 2 times, yes, 16. We don't need this because I don't have to evaluate at 0. I just need the derivative. That's the reason that we need this maximum value. It's e to the power of this times 1 over 16. And what shall we substitute instead of x to maximize this number? Let me use different color. To maximize this number on that interval. Like what we can substitute? We have to maximize. if we have interval from -2 to 2, and yes, we simply have to substitute 2. If you have your derivative and the quantity x is in the denominator somehow, we have to pick minimum value from the given interval to maximize, yeah? Because if the denominator is smaller, the whole value, the whole fraction is bigger. Yeah, just algebra reminder. But yes, this will be e. Actually, I can, to maximize this, it will be e plus 1 over the maximum number, 2 times 1 over 60. That means this number is e to the power of 1 plus 1, e squared over 16. This is a k number. Okay, that means now let's see. K number is e squared over 16. 4 factorial is 24. X minus 0 because the center is 0. Also, we have to maximize this distance. But instead of x, we can put any endpoint of the interval. That's how many units away, like what values of x we will substitute. We can substitute near to 0, yes? 0, like 0.12, but we going away, yes, we will just simply substitute 2. Yeah, this will be 2. Because then we maximizing. We have to maximize this number to have the best approximation. Okay, that's mean now we have everything. 16, 24, and 2 to the power of 4, because we also have to substitute something instead of x. Basically, that difference, this difference must be the radius. And if we have this interval, center is 0, radius is 2. Yeah, because center is 0. Okay, what is the final answer? I think this is the same, e squared over 24. And we're living in that exact form. This is the final answer. The error is less than that number. Quite small, quite good approximation. Just third degree. Yeah? No, we didn't go, yes, far. But that's, yeah, I hope you will, yes, I hope you got this question. Okay. Yeah, and I think we can finish unless we can do one more. Shall we do one more? Error? You know the polynomial. Let's do one more. Oh, I see thumbs up. Okay, because I have actually one more. This one is also a nice exam type question because we do provide a derivative. It's a weird form because it's kind of like a pattern, but it's good. You may stop you may not watch it, you may try to solve it on your own, okay? Or I will be slow, okay? Let's see. Use Taylor's inequality or error bounds, the same thing, to estimate the accuracy of approximation a function by the third degree Taylor polynomial, and the function is natural log of 1 plus 2x, quantity 1, centered at 1, and on the interval from half to 3/2, yes, from 0.5 to 1.5. That means 1 is the center and just half of the units away. And we have the fourth derivative, yeah? This is helpful information. We don't have to find the derivative. It is provided. Okay, function minus the third degree polynomial, that difference is less than the next term. 4 factorial, x minus the center to the power of 4, and k. K is also that next derivative. That means k is maximum value of the next derivative, which is also the fourth derivative. And we have the fourth derivative. Let me copy. -1 to the power. Oh, if it's the negative number, that's good. We just need the value. That means we're just taking absolute value. Yeah, don't worry for negative. That means negative doesn't matter because we'll be positive. 2 to the power of 4, 3 factorial. I can maybe write down 1 plus 2x to the power of 4. But now is the question for my students. The interval is from 1/2 to 3/2. Let me write this interval. And now, what? Yes. Well, I can see the answer. What value of x we have to substitute from that interval to maximize that quantity? We will put the lower one because x is in the denominator. It means I will substitute, let me put, I will substitute and I will put 1/2. Yeah. Shall we simplify this? I am not organizing. Maybe you know the answer. Let me say on 1/2 to 3/2. And who is first? 2 to the power of 4 is 16 times 6. Oh, this is 1. 1 plus 1 is 2. 2 to the power of 4. Oh, it's just 6. Who can confirm this? I hope. Okay. That's when we have 6, we have 24, and the same for that x. Yeah? We can just substitute either way. We can substitute this endpoint or this endpoint, because when I subtract the center, I always get the radius, and actually the radius in this situation is 1/2. That means even if we substitute 1/2 or 1.5, we will have 1/2. 1/2 to the power of 4. Okay. 6, 24, and 2 to the power of 4 is 16. We can, who can help me? Yes, because 6, I can say this is 1/4, and this is 2 to the power of 4. 16 times 4 is 64. 1/64. Or maybe I am wrong. No, 16 times 4. Yeah, this is the answer. So nice, so nice. No, it's okay. It's okay, Scott. I understand. I got 1/4 as a part. Yes, yeah. No. Okay. Yeah, I think now we can finish the session. You know the polynomials, you know the error, how to estimate the error, important, really important parts. You can practice more, but tomorrow, yes, tomorrow you will expand these polynomials to the series, but it's almost the same. You know the most important, the essential, the fundamental for this section 10.7 and 10.8. Okay, thank you very much. Thank you for your help. Thank you for joining me, and probably next week we will have our original time, which, what was the time? 10:30? I think 10:30 in the morning we will meet. Okay, but still watch the announcement. Thank you and see you next week. Thank you.